Hey everyone, welcome back. Today we're going to talk about the quotient of powers property. We're going to dive into how we use this property in order to write and simplify expressions that use exponents and division. So let's go ahead and get started. First of all, the quotient of powers property says this. When we're dividing powers that have the same base, all we're going to end up having to do is subtract those exponents. Let me show you some examples to explain why this works. In our first example, we have 2 to the 6th power being divided by 2 to the 4th power. The quotient of powers property says that we can simply take those exponents and subtract them. So we would get 2 to the 6th minus 4, which is equal to 2 squared. But why does this work? And in order to figure that out, I'm going to bring you back to exponents and what they really mean. How do we use exponents to write what we call the expanded form? When we say 2 to the 6th power, what that means, there are 6 2's all being multiplied together. 3, 4, 5, check, check, check. Okay. All of those 2's are in the numerator of this particular problem. Now let's go to that denominator. In the denominator, we have 4 2's being multiplied by each other. All we're doing is using multiplication on the numerator and the denominator both. So when we divide, what we can do is we can actually end up reducing. And we see 2 over 2. Well, 2 divided by 2, that's equal to 1. Same thing. For every pair of numbers that are the same, we end up reducing, and all they are equal to is 1. So what is left over? In this particular problem, what's left over are 2 2's still being multiplied together, but they're in the numerator position. Hence, 2 squared. Now, let's say we had more values in the denominator than we had the numerator. Using this rule, we would have a negative exponent. But what does that mean? Well, that simply means that the values we have that are left over are actually in the denominator. Now, we're not going to get into that much in this video, but it is nice to know for the future reference. Let's continue solving these problems using that quotient of powers property. In B, we have negative 7 to the 9th divided by negative 7 to the 3rd. The exponents are both talking to those parentheses, and inside those parentheses is negative 7. So we have what's called the same base. We can use this property now and just take 9 minus 3, and we get negative 7 to the 6th power. Doing it again, in C here, we have 2 h's, both with an exponent. So there's our same base, our h. We have different exponents, so let's just subtract. We have 7 h's on top in the numerator, 6 h's in the denominator. Well, we're going to end up with 1 h left over in the numerator once they all cancel. So 7 minus 6. There you go, 1. Now we don't write that 1 exponent, remember. Okay? It's kind of understood that, hey, there's just 1 h. So we don't write it. I mean, how weird would that be if we wrote the exponent of 1 for everything, for any value that we have? Yeah, that's just kind of crazy. So we don't write it. We understand it to be there. It's understood that there is a 1 exponent there. All right. Let's keep going. Now, obviously, as many things in math, this can get a little more complex. In these examples, what we're doing is we're combining what we've just learned about the quotient of powers property with our previous knowledge of our product of powers properties. So, how does this work? Well, once again, I'm going to lead you back into that expanded form to really dive into what's going on. Okay? So taking a look at A, we have 3 to the 4th power times 3 squared, all divided by 3 to the third, or 3 cubed. What does this really mean? To understand that, let's start expanding. This 4 is telling us that this 3 is being multiplied by itself 4 times. So there's 4 3s right there. This 2 is saying, hey, there's 2 3s being multiplied over here too. Both of those are being multiplied together, so we're still only dealing with multiplication in the numerator. And then we go into the denominator, and we have 3 3s, once again, all being multiplied together. Okay. Well, this is really what's going on. Okay. We take a look, and hey, I have a factor of 3 in the numerator, a factor of 3 in the denominator. We can reduce that. So any number divided by itself is equal to 1. Those all reduce down to 1. What we're going to end up with in the end here is 3 3s in the numerator being multiplied together. So 3 to the third power. Erase all that, and let's dive in using now the product of powers and the quotient of powers properties. Okay, little less work if you understand what they're saying. So the product of powers says when we're multiplying the same base, which is what we're doing in the numerator, let's add those exponents. So we have 3 to the 4th plus 2, which is 3 to the 6th. Then in the denominator, we have 3 to the 3rd. The quotient of powers property says we can subtract. So 6 minus 3, we get 3 to the 3rd power. Either way, you get the same result. That's the beauty of math, guys. Okay, multiple ways we solve the problem, get the same result. Same thing's going on with B. Okay, we can use the expanded form, or we can use the product of powers and then the quotient of powers property. Now, does it really matter which one we use first? And the answer is no. It doesn't matter if you want to use the product of powers property or the quotient of powers property first. It doesn't matter because that is all that we are doing here. Now, once we get addition, subtraction, and all those other things on operations intermixed in here, then, yeah, we have to start doing our order of operations correctly, right? But when we're dealing with just multiplication and division, they're all the same base. It's not going to make any difference because once we expand this all out, we're just going to end up with a bunch of -4s and a bunch in the numerator and a bunch of -4s in the denominator. It's all going to be the same in the end. Okay, so with this setup, you might be saying, hey, let's just take this one and simplify it. We got -4 to the 9th minus, or excuse me, we have -4 to the 9th divided by -4 to the 5th. So subtracting those, because this is a quotient now, we're dividing right there, we get -4 to the 4th. And then we can do that same thing for the second set, and we get -4 to the 6th. Now, what are we doing between these two? We're still just multiplying. So now we use that product of powers rule. We get -4 to the 10th as our final answer. Yes, those parentheses, remember, have to be there. Those parentheses tell us to include that negative throughout this entire process. So make sure we're doing that. Okay. All right. Taking a look at C now, example C. Once again, we can do it either way. Since we did this, the previous one, using the quotient of powers first, let's do the product of powers first. So we're just going to multiply straight across because we're taking a fraction times a fraction. And, well, that's the same thing as multiplying those numerators straight across and multiplying those denominators straight across. So it works. A to the 10th, A to the 7th, add those, and we get A to the 17th. In the denominator, we get A to the 10th because we got 6 plus 4 there. And now that we have a quotient, we can simply do some subtraction. 17 minus 10, oops, doesn't really look like a 10, but that's a 10, remember. Okay, 17 minus 10, we have A to the 7th power. Alrighty? Pretty easy once you get the hang of it. Now, if we were to start adding things in front of there, such as coefficients here and there, okay, we're going to treat those coefficients just like we would normally, and do one thing at a time. Well, if we're multiplying first, let's take that 3 times 6, we'll get 18. And then let's take that 4 times 2, we'll get 8. And then don't forget to reduce those independently. Okay. All right. Let's take a look at how this works in the real world setting. So modeling real life with this. In this example, we have a projected population of Tennessee for the year 2030 to be about 5 times 5.9 to the 8th power. And our job is to predict the average number of people, whoops, yes, we can spell, hold on. Okay. The average number of people per square mile in Tennessee in that year of 2030. First of all, some information that we might need to know for this. Of course, we need that area of Tennessee. So we got the land area to be about 5.9 to the 6th power miles, square miles. Okay. And we also need to know this. In order to find the average number of people per square mile, we can do that by dividing the projected population, which they gave us up here in the word problem, divide that by our land area. Okay, well, all right, let's get to it then. We've got our projected population. We're guessing here, right? We're projecting it to be this. And we're going to divide that by the amount of land we have in order to predict the average number of people per square mile. So it's people per square mile. Well, this is representing our amount of people that we're predicting to have, and this is our amount of land that we have. Okay? So per square mile. First of all, reminder, the quotient of product property only works with the same base. So we're going to focus on this 5 9/10 base. Okay? We're going to kind of brush that other extra 5 out of the way, and we're going to focus right here when my bases are equivalent to each other. And actually, we're just going to pull that 5 out in front because we're not going to touch it right now. And then let's do this. So quotient of product, well, we're going to take 8 minus 6, we'll get 2. So we have 5 to the 9th squared. Our answer is going to be 5 times 5 to the 9th squared, or excuse me, 5.9 squared. All right. Doing that calculation, we end up with about 174 people per square mile. I showed you several examples on the quotient of power property, how it can work. So let's let you give it a shot. Here's a couple problems for you to try. Pause the video, try them out, and I'll be back with the answers. Now that you've given it a shot, let's see how you did. For number 1, we have -3 to the 7th power as our answer. Number 2 is 8 cubed. Number 3 is simply just x. Number 4 is 5 to the 6th power. Number 5 is that -2, yes, in parentheses, to the 5th power. Number 6, we have b to the 13th. Now let me talk about number 7 here then. All right. For number 7, we have a crate that we're fitting cube items in. So first we have to realize that this crate is going to hold these cubed items, okay? All right. Now, then it goes into a couple more details. Well, first of all, let's take care of this item. They're calling it the box, okay? In order to write an expression for the number of boxes that can fit in the crate, we have to understand the volume of each box. So how do we find volume of a box? Well, volume is length times width times height. Or we can think of volume as the area of the base times the height. But here we have cubes. So we need to realize that cubes, all sides are equal. So the length is S, length, the width is S, and the height is S. All of them can be represented using S is generally what we do for side. Okay, so what is the volume of a cube? It's S cubed. All right, so that's our volume of the cube. Or they say box. Okay, now let's talk about the volume of the crate. And once again, I know I can spell correctly. Sorry about that. Okay. So they're saying that this crate is this box squared. Okay, so this crate is this box squared. Well, to find the volume of the crate, we would take the volume of the box then, and hey, we're going to square it because that's what they told us to do. Okay, if the length is squared, the height is squared, and the width is squared because they're both going to be cubes. That would mean that the volume of the crate is equal to S to the 6th power, whatever the side length is. Now, how many boxes would fit in one crate? Well, a crate is S to the 6th. A box is S cubed. Fitting something into another, well, we're going to use some division there. And we're going to say, all right, the crate divided by the box. How many boxes are in the crate? And we're going to say S cubed. Whatever the side length is, cubed. Okay? That's the number of boxes that can fit into this crate. Yay! Well, thanks for joining me once again on a quest of mathematical knowledge over the quotient of powers. Until next time, this is Mrs. Struble with Struble Math. Bye.